Last chapter we studied about basics of semiconductor, and in this chapter we will study about the p-n junction diodes. A p-n junction diode is basically a semiconductor material, semiconductor device in which both p-type and n-type semiconductors are joined. There are different types of junctions can be formed based on different manufacturing process, fabrication process, which will be discussed later on. At the starting, we will consider that a p-n junction can be formed by joining a p-type semiconductor and an n-type semiconductor. In p-type semiconductor, we have already seen its representation. There will be negative ions and the majority charge carriers will be holes. While there will be few minority charge carriers, that is electrons. In n-type semiconductor, in the representation, we already seen that there are positive ions in n-type semiconductor and the majority charge carriers are electrons. With these electrons, there will be some holes also. So we can say that in n-type semiconductor, the electron concentration is far greater than the electron concentration in p-type semiconductor. If we move from n-type to p-type semiconductor, the electron concentration in n-type semiconductor is far greater than in p-type semiconductor. So electron concentration decreases as we move from n-type to p-type semiconductor. While if we move from p-type to n-type semiconductor, the whole concentration in p-type semiconductor is far greater than the whole concentration in n-type semiconductor. So we can say that the whole concentration decreases as we move from p-type to n-type semiconductor. As there exists a concentration gradient for holes between p-type and n-type semiconductor and electrons between n-type and p-type semiconductor, the charge carriers will cross the junction, which is the boundary between n-type and p-type semiconductor. The holes from p-type to n-type semiconductor will cross the junction and move towards n-type semiconductor, and the electrons from higher concentration in n-type semiconductor to lower concentration in p-type semiconductor, these charge carriers will cross the junction and will move from higher concentration to lower concentration. If holes are moving in this direction, electrons are moving in this direction, and at the junction there is a chances of recombination between these charge carriers, and there will be a large number of recombination, and due to the recombination large number of bonds will be formed, and a region is formed near the junction which consists of positive ions on n side and negative ions on p side, while the rest of material will be as it is. In the rest of material, charge carriers electrons are available, but in the depletion layer, in this particular region which is called depletion layer, in this layer there are no free charge carriers, and as it is depleted of charge carriers, it is called depletion layer. On p-type semiconductor, the structure will be as it is. There will be majority charge carriers, holes, and there will be very few electrons. As in the depletion layer, we can see that there are positive ions on N side and there are negative ions on P side. So the depletion layer, in the depletion layer, there are positive ions on N side and negative ions on P side. So there will be a potential difference on either sides of the between either sides of the depletion layer, and this potential difference is represented by V naught. Now, due to this potential difference, an electric field will induce across the depletion layer, which directs from positive to negative, means from N side to P side. This electric field directs from N side to P side. Now, suppose this is a material. This is a material in which we have applied an electric field. Holes will move in the direction of electric field while electrons will move in the opposite direction of electric field. This will be the direction of charge carriers on the application of electric field. Now in this material, an electric field is induced across the depletion layer. Now if hole try to diffuse from higher concentration to lower concentration in this side, then this motion will be against the motion of hole under the effect of electric field. So this hole will not be allowed to move from P side to N side. While this electron in the N-type semiconductor will try to cross the junction from higher concentration to lower concentration. Again, the motion of electron is in the direction of electric field, which is opposite to this convention. So this electron will not be allowed to move in the from the N side to P side. So we can say that the electrons in N-type semiconductor and holes in P-type semiconductor will be restricted by the depletion layer. Will not be allowed to cross the junction. While electrons in the P-type semiconductor and holes in the N-type semiconductor are free to cross the junction. So depletion layer will not restrict minority charge carriers to cross this junction. Now we will plot charge density in the depletion layer. On the P side there is negative ions, so charges will be negative, and on the N side there are positive ions, so charges will be positive and charge density will be like this. On N side there is positive charge density and on P side there is negative charge density. Now we will plot electric field intensity. Electric field has graph as electric field is plotted below zero line because the conventional direction of electric field is from P to N, but actual direction but the actual direction is from N to P. Hence, it is floated in negative axis, negative direction. It has maximum magnitude at the junction. Means electric field is maximum at the junction and zero at the ends of the depletion layer. Zero at the ends of the depletion layer. This is the plot of electric field for a PN junction. We will revise all the things. First, we join a p-type semiconductor with n-type semiconductor. A junction is formed between them. On p side, majority charge carriers are holes, and on n side, majority charge carriers are electrons. There are very few electrons on p side and there are very few holes on n side. Due to higher concentration of holes on p side with respect to n side, these holes will diffuse towards n side and these electrons will diffuse from higher concentration to lower concentration towards p side, and there will be large number of recombinations and a depletion layer is formed near the junction. This depletion layer will consist of positive ions on n side and negative ions on p side. This depletion layer has positive charge on n side and negative charge on p side, and due to this potential is developed across the depletion layer, and due to this potential an electric field will induce which directs from n side to p side. This electric field E will restrict majority carriers to cross the junction, while this electric field does not restrict minority carriers to cross the junction. So this electric field will prohibit further diffusion of majority charge carriers across the junction, and a PN junction will be formed as shown in the figure. The width of depletion layer in PN junction diode. Suppose this is PN junction diode. In this PN junction diode, there will be a depletion layer at the junction, and the width of depletion layer is mathematically given by W equal to under root of twice epsilon upon Q into 1 upon Na plus 1 upon Nd into V0, where epsilon is called permittivity and epsilon is written as epsilon naught into epsilon r. Epsilon naught permittivity of free space, and epsilon r is relative permittivity of the semiconductor. Na is doping on P side, Nd is doping on N side, and Q is electronic charge 1.6 into 10 raised to power minus 19 coulomb, and V0 is called contact potential or built-in potential or junction potential. junction potential, and this contact potential is mathematically given by V naught equal to Vt log to the base e Na into Md upon Ni square in volts. This is the equation for contact potential V naught. The typical values of this contact potential is around 0.1 to 0.3 volts for germanium, and it is around 0.6 to 0.5 to 0.9 volts for silicon. The value of this contact potential varies in the range for different materials, germanium and silicon. Now, the symbol for PN junction diode we will use in our circuit. There will be two semiconductor layers. This layer will be called P-type semiconductor, and this layer will be N-type semiconductor. And arrow will be shown in this direction from P to N. This shows direction of current when it is forward biased. The terminal of the diode on P side is called anode and will be represented in the circuits with A, and the terminal of the diode towards N-type semiconductor called cathode is represented with K. Now we will study the biasing of the PN junction diode, and we will study the VI characteristics of diode. First is PN junction in forward bias. PN junction in forward bias. A PN junction is said to be forward biased when P side is biased at higher potential with respect to N side, or anode is biased at higher potential with respect to cathode. Then PN junction can be said to be forward biased. In the circuit, we will show a forward biased PN junction as this is P side and this is P side and this is N side. This is anode terminal and this is cathode terminal. We will connect the battery in such a way that anode is biased at higher potential with respect to cathode, and in this figure it is clearly seen that the battery is making anode at higher potential with respect to cathode. This resistance R is called current limiting resistance. Current limiting resistor. Now we will see the internal structure of diode when it is forward biased. This is the PN diode and it is forward biased. P side and N side. P side there will be negative ions, on N side there will be positive ions, and there will be a contact potential and an electric field which varies from N side to P side. Now on P side, majority charge carriers are holes. I'm not showing negative ions because they are of no use while explaining this operation of the PN junction. On N side, there are majority charge carriers, electrons, and very few holes are there, and very few electrons are there on P side. Now, if this junction is forward biased, the electric field which was already there at across the location there, this electric field can allow only the flow of holes in the direction of electric field. If hole tries to move opposite direction, this field will restrict this hole, and this electric field can allow electron to move in this direction, and if this electron tries to move in this direction, it will be restricted by the electric field. Now, seeing the polarity of the supply, due to this polarity, an electric field will induced across this PN junction diode. This electric field will uh, cause the holes to move in this direction while electrons in this direction. But just now we have studied that this electric field will not allow this hole to move in this direction, and this electric field will not allow electron to move in this direction. So first, the supply voltage should be that much stronger. Supply voltage should make this electric field be more stronger than this electric field, so that the flow of charge carriers can start. Earlier, when applied electric field EI is less than E, then flow of charge carriers, flow of majority carriers will not be allowed. Flow of majority charge carriers will not be allowed. So we can see that if EI is less than E, flow of majority charge carriers will not be allowed, and current IF in forward will nearly equal to 0. Now, if applied electric field EI is greater than E, means applied electric field becomes greater than E, then majority carriers will cross the junction, and a large forward current flows to diode given by IF equal to I naught into e raised to power Vd upon eta into 50. This was the PN junction which was forward biased, and this PN junction, across this PN junction, when we apply a supply voltage, there will be some voltage drop Vd, and this voltage drop is considered in this equation, while the current flowing through this diode will be called IF, and this equation is written for this current IF. I naught is called reverse saturation current. Will be explained later. Vd is called forward drop, voltage drop. It is a voltage drop across diode. eta is called ideality factor, ideality factor, and its value equal to 1 for germanium and its value equal to 2 for silicon. Vt is called thermal voltage. It is called thermal voltage. Now we will see exactly what happens when a diode is forward biased. In the recent 2-3 years, this question was asked in the GATE examination. The nature of the current was asked in a forward biased PN junction. Now, a PN junction is forward biased. In P side, majority charge carriers are holes, and on N side, majority charge carriers are electrons. Now, when this junction is forward biased, these electrons, these holes will cross the junction and will be injected on the N side, and these injected charge carriers will accumulate near the junction, and these electrons will be injected into P side, and these electrons will accumulate near the junction. These and these are called injected minority charge carriers. These are called minority charge carriers because holes in N-type are minority charge carriers. Now, these injected charge carriers has a very high concentration in this region, in this particular region, and if we see the whole concentration in rest of the material, it is very less as compared to the whole concentration in this particular region. So these holes will diffuse from higher concentration to lower concentration. So in forward bias PN junction, first there was injection of charge carriers and there was diffusion then. Similarly here, the electron concentration is very large as compared to electron concentration in rest of material. So these electrons will move from higher concentration to lower concentration, means there will be diffusion of these electrons. So for these electrons there was first injection and later diffusion. As the charge carriers after injecting from one side to other side are diffusing, so I can conclude that forward current of diode is a diffusion current. So in a forward biased PN junction, the current will be a diffusion current. Majority charge carriers will be first injected and then these charge carriers will diffuse from higher concentration to lower concentration. In this way, a PN junction diode in forward bias will conduct. Now we will draw VI characteristics of a forward bias PN junction. VI characteristics of a forward bias PN junction. In a forward bias PN junction, the VI characteristics are obtained practically by supplying, by connecting the battery as shown in the figure. The voltage across diode Vd is varied and current IF through diode is measured. IF versus Vd are the forward characteristics of diode. The forward characteristics of diode are as shown in the figure. The current through diode is nearly equal to 0 unless the electric field across the junction is overcome by the applied electric field. So the current through diode up to certain voltage Vd will be nearly equal to 0. So this voltage will be defined as V gamma, called cut in voltage of diode. And this cut-in voltage is nearly equal to 0.2 volt for germanium and nearly equal to 0.7 volt for silicon. Now, if applied Vd is less than V gamma, applied Vd is less than V gamma, the current through diode IF will be nearly equal to 0. And if applied voltage is greater than equal to V gamma, IF will be equal to I naught into e raised to power Vd upon Vd. Means the forward current will depend on forward voltage Vd if Vd is greater than V gamma. Now, one more thing happens in a forward biased PN junction. When a PN junction is forward biased, with change in applied voltage, or more precisely with increase in applied voltage, the depletion layer width at the junction decreases. Means the depletion layer width of a forward biased PN junction is less than the depletion layer width of unbiased PN junction. So we can say that the depletion layer width W is inversely proportional to forward biased voltage. We don't have exact equation, but depletion layer width decreases with forward biased voltage. Now we will study PN junction diode biased in reverse direction. A PN junction is said to be reverse biased only if N side is biased at higher potential with respect to P side, or cathode K is biased at higher potential with respect to anode. Then only we can say that a PN junction is forward biased. In a forward biased PN junction, shown in the figure, a PN junction can be reverse biased by connecting the battery terminals shown in the figure. When PN junction is reverse biased, the current will flow in this direction will be called reverse current IR. Now we will see the internal structure of diode, which is reverse biased. On the N side, majority charge carriers are electrons, while there are few holes. While in P-type semiconductor, there are majority charge carriers are holes and there will be few electrons as minority charge carriers. Now, when this junction is reverse biased, means N side is biased at higher potential, these holes will move from higher potential to lower potential. This was the junction across field, and this will be applied electric field. Both are in same direction, therefore the effect of both will be addition of both on charge carriers. So these holes will move from N side to P side, while these electrons will move from P side to N side. As we can see that the charge carriers which are crossing the junction has a concentration very less, that is minority charge carriers are taking part in conduction. As minority charge carriers are taking part in conduction and as their concentration is very low, the reverse current IR is very less and its equation is given by IR equal to I naught into e raised to power V. This will be reverse voltage VR upon eta into Vt. This equation to be used. Where minus 1, this equation will be used. Sorry, I have made a mistake while defining the current in forward direction. I will correct it later. IR equal to I naught into e raised to power VR upon eta Vt minus 1. This voltage VR will be a negative voltage, so I can say that this will be I naught into e raised to power minus VR upon eta into Vt. Biased in the reverse direction, so I have written a voltage negative here. Now e raised to power minus VR upon eta into Vt is a negative exponential, and this the value of this negative exponential will be surely less than 1. If it is less than 1, then the current IR will be equal to minus 1. If I show this direction of IR in this direction, IR, then this equation for IR can be used, and according to this equation, the actual direction of IR is in opposite direction due to this negative sign, and this reverse current has magnitude I naught. So I can conclude that in a reverse biased PN junction, reverse current flows which has magnitude I naught. Direction will be opposite to that of forward current. So in reverse biased PN junction, as minority charge carriers take part in conduction, the current will be very less and it is given by I naught. The forward current equation, actually I gave equation which was approximated. The actual current equation for forward current is IF equal to I naught into e raised to power Vd upon eta Vt minus 1. Here this part is positive. This part is positive. As this part is positive, e raised to power Vd upon eta Vt will be a positive exponential and surely it will be very greater than 1. So I can neglect this one and can write IF nearly equal to I naught into e raised to power Vd upon eta Vt. Same equation used for reverse bias condition. Now, unlike in forward bias PN junction, there was no diffusion of charge carriers during the conduction. From N side, holes were crossing the junction, and from P side, electrons were crossing the junction. Here, the hole is moving from lower concentration to a region where hole concentration is very high. So this current cannot be a diffusion current, while this electron is moving from P side to N side into a region where electron concentration is already very high. So I can say that the during conduction in a reverse direction, the minority charge carriers cross the junction from higher concentration to lower concentration, and it can be said that the reverse current cannot be a drift current, sorry, cannot be a diffusion current, as in the case of forward bias PN junction, so reverse current is a drift current. It can be asked in the examination, the nature of reverse current is drift current. Now we will draw VI characteristics for a reverse biased PN junction. Now for this reverse bias PN junction, this is the voltage across this PN junction VR. It was VD in the case of forward bias PN junction, and it is VR in the case of reverse bias PN junction. And this voltage V is applied. Due to this voltage, a small current flows through the diode, which is equal to I naught called reverse saturation current. So in reverse bias PN junction, it conducts very less and a very small current flow through the diode. This current is called I naught reverse saturation current, and its value is in microamperes for germanium, and it is in nanoamperes for silicon. The magnitude of this reverse current is large in case of germanium in microamperes as compared to nanoampere in silicon. This is the greatest advantage of silicon over germanium, that its reverse saturation current is very less as compared to reverse saturation current in germanium diode. Now we saw that in a forward bias PN junction, with increase in forward voltage, the depletion layer first decreases. Exactly opposite to that, when a PN junction is reverse biased, this is P side and this is N side. If PN junction is reverse biased, the depletion layer increases with the applied reverse voltage, and its relation with the applied reverse voltage is given by W is equal to under root of twice epsilon upon Q into 1 upon Na plus 1 upon Nd into V0 plus Vr reverse bias voltage. Now from this equation, if I consider all the things are to be constant, I can say that depletion layer with W is directly proportional to root of V0 plus Vr. As Vr is very greater than V0, I can say W is directly proportional to root of reverse bias. So for a PN junction biased in reverse direction, the depletion layer width is directly proportional to root of reverse bias voltage. Means the depletion layer width will increase with increase in reverse bias voltage. Now, when this diode is used in practical circuits, we will have to replace this diode with its equivalent circuit. So now we will draw equivalent circuits of diode. Equivalent circuits will be based on the biasing of diode. If diode is forward biased, it will be replaced by different components in the circuit. If diode is forward biased, that is its anode terminal is biased at higher potential with respect to cathode terminal. As according to definition, a diode conducts only in forward bias case. So seeing this diode as ideal, I will expect an operation that it should operate like a short circuit. So in a forward biased PN junction, it is replaced in the circuit with a short circuit when it is forward biased. And when in the question material of the diode is given, or I will say if the diode is practical, practical is identified with either material is given or forward drop is given. If any of the quantity is given, any of the thing is given in the problem out of these two, the diode will be considered as practical diode. And for the practical diode, it cannot conduct until the applied electric field overcome the induced electric field across the junction. So, in other words, I can say that diode cannot conduct until the applied forward voltage overcome the cut-in voltage of diode. So, uh, in this case, the diode will be replaced with a battery which is opposing to the supply voltage, and this battery has potential equal to V gamma. This is anode terminal, this is cathode terminal, and this V gamma equal to 0.2 volt for germanium and will be equal to 0.7 volt for silicon. This will be for germanium and zero point 0.7 volt for silicon. Last case, in some cases, forward resistance of diode is also given. Means a diode is operating in forward bias and offering some resistance. Obviously, it will be very small, but if it is given in the problem, it should be considered in the equivalent circuit of diode, and diode will be replaced with this forward resistance RF and cutting voltage V gamma. These are the equivalent circuits of a diode when it is biased in forward direction. If diode is ideal, it will be replaced with a short circuit, and if it is a practical diode, it will be replaced a cut-in voltage, a battery with cut-in voltage, and if forward resistance is given, it will be replaced with series combination of forward resistance RF and cutting voltage V gamma. The value of this resistance will be low. Second case, if a diode is reverse biased, we will have to replace it with its equivalent circuit. I will replace, I will interchange the terminals of diode. This is cathode terminal, this is anode terminal. For suppose this diode is reverse biased, and in the problem it is given that it is ideal diode, or even it is practical diode. In both the cases, when it is reverse biased, it will be replaced with a open circuit. This is cathode terminal and this is anode terminal. This means that a diode which is reverse biased does not conduct. It will be replaced with an open circuit. And next case is if diode is little bit conducting, means it is offering a very high impedance. In case of open circuit, impedance is infinite, but if if it is offering a finite resistance which is given in the problem, that is reverse resistance RR, which will be very high, is given in the problem, then we will have to replace this diode with this resistance RR. Means diode is behaving like a very high resistance when it is operating in reverse bias, and ideally it is replaced with the open circuit, means it is not allowing to any current to flow through the diode. These are the equivalent circuits of the diode. When we will use this diode in practical circuits, it will be replaced with these equivalent circuits. We will see some examples. Calculate V and I. Calculate V naught and I. This is V naught and this is current I. Applied voltage is 30 volts. In this problem, uh, we are not given any specification about diode, and material is not mentioned, and no forward drop is mentioned. So we will consider the diode as ideal. Considering the diode as ideal, If it is ideal diode, it will be replaced with a short circuit when it is operating in forward bias. In the circuit, it is clearly seen that this diode is forward biased, so it will be replaced with a short circuit, and this resistance is 1 kilo ohm. So I can calculate the current through the diode I by applying the KVL minus 30 plus this current will flow through this diode and a voltage drop will be there. I into 1 kilo ohm equal to 0. So I will be equal to 30 upon 1 kilo ohm will be equal to 30 milliamperes. And we can see that across these two terminals plus 30 volt is applied, and the whole plus 30 volt is going across the output terminals. So the output voltage V0 will be equal to 30 volts. Next question. Calculate I and V0. In this problem, in this problem, with the diode, its material is mentioned. As material is silicon, its cutting voltage V gamma will be equal to 0.7 volt. So in the circuit diode, first we will check that it is forward biased or reverse biased. According to the polarity of the battery, it is clear that this diode is forward biased, and we can replace this forward biased P injection with its cutting voltage, which is equal to 0.7 volt. Now it is clearly seen that across these two terminals we are calculating the output voltage, and across these two terminals a battery is connected between them, zero point 0.7 volt. So it is clearly seen that V0 equal to 0.7 volt. Also current I can be calculated as minus 30 plus I into 1 kilo ohm. This will be current I through this resistance, and this will be voltage drop across this. Minus 30 plus I into 1 kilo ohm plus zero point 0.7 volt equal to 0. From this KVL equation, I will calculate 30 minus zero point 0.7 divided by 1 kilo ohm equal to 29.3 milliamperes. This will be the current through diode, and this is the voltage across the diode. Next, in this question, we are asked to calculate a V0 voltage, and the parallel combination of two germanium diodes is used. From the supply voltage, it is clearly seen that both the germanium diodes will be forward biased, and we can replace both the diodes with their equivalent circuits. As material is mentioned, but these two diodes will be replaced with their equivalent circuits, that is 0.2 volts. And now the voltage V0 can be calculated. V0 can be calculated. First, we will have to calculate the current, or another technique is there to calculate V0. We will replace this V0 with a battery for some time to calculate V0. I will replace this 10 volt with a battery, and other end will be grounded. This is 10 volt battery, and I will apply a KVL in this loop and calculate V naught. With the KVL equation in this loop, minus 10 volt plus 0.2 volt plus V naught equal to 0. Therefore, V naught will be equal to 10 minus 0.2 equal to 9.8 volts. V naught will be equal to 9.8 volts. Next question. Now, calculate V naught in this circuit. There is a parallel combination of a germanium diode and silicon diode. When two diodes are connected in parallel, one is germanium diode and other is silicon diode. If we will replace both the diodes with their equivalent circuits, as it is clearly seen that both the diodes are forward biased, if we replace both the diodes with their equivalent circuit, one will be replaced with the 0.2 volt germanium diode and other will be replaced with 0.7 volt. In this particular part of this circuit, there are two parallel branches, one is this and one is this. In these two parallel branches, there are different voltages. But according to KVL Kirchhoff's voltage law, in parallel branches, there cannot be two different voltages. So either this diode will be off, either or this diode will be off. So both the diodes connected in parallel cannot conduct at a time. You can remember for this concept for solving any other problem, that if two diodes are connected in parallel, then only the diode with lower cut-in voltage will conduct. If the diode with lower cut-in voltage will conduct, then we will draw the circuit as germanium diode has lower cut-in voltage 0.2 volt while silicon diode has higher cut-in voltage, so it will not conduct, and if diode is not conducting, it will be replaced with an open circuit. It will be replaced with an open circuit. Now I can replace this 10 volt with a battery, and I can replace this V0 with a battery. Now I can calculate this voltage V0 by applying loop KVL in this loop. Minus 10 volt plus 0.2 volt plus V0 equal to 0. Therefore, V0 will be equal to 10 minus 0.2 volt equal to 9.8 volts. 9.8 volts. Now, next problem. For a PN junction, Na equal to Nd equal to 5 into 10 raised to power 15 per centimeter cube, and Ni equal to 1.5 into 10 raised to power 10 per centimeter cube. Calculate V0 at T equal to 300 degrees Kelvin. Assume Vt equal to 25 millivolt. We have to calculate contact potential V0. We know that contact potential V0 equal to Vt